Okay, so I'm very excited. We're continuing our tutorial 6 of the summer school. Very excited to have Zilinghan from Argonne. He's a machine learning engineer in the data science and learning division and works with biomedical. And I think they also recently got a NIRE pilot award on federated learning. And so they're going to share with us about federated learning and how we can leverage that for privacy preserving learning frameworks. So with that, I hand it over to you.
Thanks. Thank you for the introduction, and it's glad to present on behalf of our senior computer scientist at Argonne, Ravi Maduri, to introduce federated learning from its concepts, applications, challenges, and our effort in building a framework for it. So now let's finally jump in and first talk about what is the motivation for federated learning. And we can start from a very, very extreme case. So me at the Argonne, I come up with ideas, say I want to train a digit classifier. And I ask some data team at Argonne, say, yeah, I want to do this. Please collect me some data. And data team says, yeah, this is a really good idea. It's an innovative idea. Okay, I help you to collect some data. And finally, they get back to me, say, I only collect image for digits 0, 1, and 2. Say, this is all we can get you. And in this case, no matter how many effort I put, what kind of tricks, strategies, machine learning model I use, I cannot get a good model because I just have these 3 digits. My classifier can only classify with 0, 1, 2 correctly, but not 3, 4, all the way to 9. So in this case, what should I do? So I come up with an idea. I contact someone at the University of Michigan, say, could you please also help me to collect some data on your side? And they say, yeah, this is a good idea. And they ask their data team at the University of Michigan and get back to me that they collect some data for digits 3, 4, and 5. And it's better, but it's still not enough. So I reached out to someone at the University of Illinois, say, could you please also collect me some data? And he says, okay, I collect 5, 6, 7. One step further, I got someone at the University of Chicago and say, also help me to collect some data, and we finally get 7, 8, 9. So now we have all 10 digits. And ideally, we want to collect all this data into a central data repository. So we are all going to collect a digit image classifier. But here's the problem. The Argonne administrator from the data team says, no, you cannot, we don't allow you to share this data. This data are private to Argonne. If you share this data, like it is, it's like against our privacy preserving some things. So you cannot share. And also, an administrator at all other 3 institutes said the same thing. You cannot share the data. So in this case, what should we do? So the idea for federated learning just comes is that can we share the model trained on the local data instead of sharing the data directly? So all 4 institutes, they train the same machine learning model at the beginning on their local data, and they share those model parameters to a central place, like a central server, to aggregate those model parameters, and then send that aggregated model parameters back. And then by each institution do further round of local training, shared again and again. So in this case, these 4 clients, we call it, they create a loose federation to collaborate to train the same machine learning model, and we call it federated learning. And you may wonder, yeah, this sounds strange. Like each institute, they train only on like 3 labels. Can this perform well? And let's see whether it performs well or not. So this distribution shows a partition of the image minutes data set, which is a digit image data set. And for each row, it is the data distribution of a single site or single data silo. And we can see that each site only has like 3 to 5 labels, and they are pretty unbalanced and independent, identically distributed. But if we train federated learning, we train using federated learning for CNN by sharing the model parameter, we can get more than 95% accuracy. So actually it works. But this example is kind of trivial, and it may not convince you that federated learning is important, because real world does not sound like this, right? It's not the case that each institute just have like data for just 3 digits. But so why we still need federated learning? This is because in the real world, it's common that the data at different data silos have different distributions. So let's see some examples. Here are like, here we have 2 data silos, or we say 2 clients. And here and each client has an image data set on their local data silo. And we can see the RGB distribution of these 2 data sets. They vary a lot. And here, this is the density and intensity plot for other type of data for force clients, and they also have some variations. The same thing for this third plot. And this one shows the UMAP dimension reduction of data at 6 clients, and we see that each site kind of has its own distribution cluster. Also, this is a survival probability data set as 6 clients, and we can clearly see that they have completely this data distribution. And same thing for this electronic health record data set. For the age, blood pressure, and heart rate, we can see different data sets have different distributions for these values. So as you can imagine, with this type of data set, if you only train a machine learning model using the local data set, they may not generalize well on other data sets. So we always want to leverage as much data as possible to train a more robust and generalized machine learning model. But the problem is that in biomedical or other domains, there are a lot of privacy concerns for sharing those data. So in biomedical, for example, access to many types of data like EHR, medical images, ECG readings are restricted by different laws at different places of the world. So it is very, very difficult or impossible to share this data with other institutes for training a more generalized machine learning model. So federated learning should be a promising approach to tackle these privacy concerns and get a more better model. And also, FL can be used in training foundation models to leverage a large amount of private data at distributed data silos. So nowadays, more than 80% of data are privately stored in private data silos. And so when we want to train a more robust foundation model, in addition to trying the effort to make the foundation model larger and larger, the amount of training data is also one of the key factors to success, and federated learning can be utilized to leverage more training data and help us to get a better foundation model. So after talking some motivations for federated learning, let's just introduce federated learning again. So in federated learning, it has a central server and several clients, and each with their private local data set. And they have their own computing resources, and these can be heterogeneous. Some can be HPC with Slurm scheduler, some can be on the cloud, like Google Cloud, AWS. And in each training round, the client trains a machine learning model using their local data set and share it with the server. The server aggregates those model parameters. By aggregates, the easiest aggregation can be the weighted average of those model parameters, and then send back the updated global model back to the clients to perform another round of local training, send back to the server again for aggregation, and so on and so forth. And this is federated learning. And now we can introduce some application of federated learning. This one is the detection of COVID-19 from chest X-rays. And in this case, we have 2 data silos or 2 clients. The first one, we call it ANL, Oregon National Lab COVID dataset. This dataset is aggregated from multiple open source data sets. And we have another private data set from University of Chicago Medical Center, which is a privately collected by UChicago. And then we train 3 models. One is only trained on the ANL COVID data set. One is only trained on the UChicago data set. And one is trained using federated learning by using these 2 data sets. And the results on the right-hand side shows that using federated learning, we can get a better like classification model on some general like holdout validation data sets. And it can also, we also apply federated learning in biological aging prediction from the electrocardiogram signal. In this case, we also have 2 data sets. One is aggregation of open source data set collected by ANL, we call it ECG ANL. And one is a private data set from the Broad Institute of Harvard and at Harvard and MIT. So we also trained 3 models here. One is using the ECG ANL data set. And when we train with this data set, and we use a holdout testing data set at the ANL, it can get something around 100 mean square error on the ANL testing data set. However, if we test this model on the testing model on the testing data from the Broad Institute, the MSE gets extremely larger. The same thing, if we train a model using the Broad Institute data, then it gets good accuracy on the broad testing data set, but it does not generalize well on the ANL test data set. But if we use federated learning using these 2 data sets, it can get good performance on both the ANL test data set and the Broad Institute test data set. We also have some use case to fine-tune a large language model for various downstream tasks. And we compare federated learning with centralized training, which means we collect all the data to a central location, and local training, which means we only train the model using the local data. The green lines are the accuracy of local training, orange lines are federated learning, and the blue line are centralized training. So we can see that there is a non-marginal gap between local training and federated learning, and there's a relatively small gap between federated learning and centralized training, and this shows the advantage of federated learning, that it can utilize more data to get a better model without direct data sharing. We also utilize this to forecast energy consumption in electric grids. And we can see that without federated learning, we are far from the ground truth, but with federated learning, we can get pretty close to the ground truth of the energy consumption. So after talking about these applications in different domains where data privacy can be a problem, then we can talk about what are the challenges in federated learning. So due to the distributed nature of federated learning, it suffers a lot from heterogeneity problems. And one of them we already mentioned is the data heterogeneity. We see that in federated learning, maybe not that extreme, but the data is usually unbalanced and non-IID distributed. And this causes that different clients have different local training objectives, and their trained model can drift away from each other. And this may cause a global model to become something that contains some garbage model parameters. So how should we avoid this? One type of solutions is using some server-side momentum or other optimization strategies to avoid the global model change drastically in each training round. So in traditional Fed average, it is the central server collects the model gradients from different clients and take a weighted average of those model gradients and apply those model gradients to the global model. But if we apply with some momentum for the model gradients, we can try to make the global model does not change too much in each training round, and this can somehow alleviate the data heterogeneity problem. And the second type of solution is adding a proximal term in client local training objective, or it is like the regularization. We add this term, this proximal term in the local training loss function. where W is the local model parameter and WT is the initial global model parameter. So with this loss function, we can force the local trained model to not change too much or drift away from the initial global model. And this can also help us to alleviate the data heterogeneity problem. And the second type of heterogeneity is device heterogeneity. So in federated learning, each client, they train the local model on their own computing facilities. And it is the case that these computing facilities can be heterogeneous, as I mentioned. Some can be on HPC, some can be on cloud, and for different HPC, right, they have different amount of number of GPUs or GPU memory. So the computing power can be different. And as a result for that, for each client, if they train the local model for the same amount of data, they may take like significantly different amount of time to finish the local training job. So for some synchronous FL algorithm, where the server has to wait for all clients to send back their local models, they suffer a lot from the resource wastage. We can see this from the plot on the right-hand side. So we have two clients. One is client one, it has a relatively less powerful computing machine, and client two has more powerful computing resources. So training to train a local model, client two only takes 15 minutes to finish one round, while client one takes 1 hour. However, if we do everything in a synchronous way, then the server has to wait until 1 hour to aggregate these two model parameters and send the updated model back to the clients for further round of local training. And this caused a lot of resource wastage for the more powerful machine. And this can be a problem. This significantly reduces the efficiency of the FL experiments. So how can we do that? How can we resolve this problem? There are some asynchronous federated learning algorithms are proposed, which basically updates the global model immediately once receiving the local model from each client. But this solution also suffers from the stale local models from the slower clients. And what does that mean? So we have the same two machines in the first in the synchronous case. And at time 0, both clients have model 0, or say model with time step 0. And after 15 minutes, client 2 finish local training and send its updated model to the server. And the server just use this one local model to update the global model. And the server model is updated to model with time step 1. And then it sends this back to the client 1, to the client 2. And then client 2 get model 1 and immediately starts the next round of local training. And at time 30, client 2 finish again and send the updated model back to the server. Server update the model parameter to get model 2, send it back to client 2, and then client 2 started another round of local training. And at time 45, client 2 finish again and send the model 3 to the server. The server send it back for a further round of training. And after 1 hour, client 2 finish the 4th time and send it to the server. The server updates the global model to model 4 and then send it back to the client. And finally, after 1 hour and 5 minutes, client 1 finally finished its first round of local training. But the problem here is that this local model is trained on model 0, but the global model is already updated to model 4. So we call this local model stale local model. It is too old. And if we use this local model to update the global model, it can be detrimental to the global model. It can reduce the accuracy of the global model. Or some people say, okay, in this case, right, I want to use a small importance weight to this stale local model. But just think of it, right? Client 1 is very, very slow. And then you apply another small importance weight to it. Then the global model is almost like the model at client 2. And the global model is drifting far away from the data on client 1. And this is a problem. So in this case, right, we may not get a robust global model. So how can we resolve this problem? So here is some intuition for our solution. Can we try to synchronize the arrival of clients' trained local model by assigning different number of local training steps to them according to the client's computing power? So if we assume that we know the underlying computing power of different clients ahead of time, then we can assign steps accordingly to their computing power. So in this case, right, so if client 1 has computing power 5, client 2 have power 2, client 3 have power 1, and client 4 have power 4, then we can assign training steps accordingly so they can finish approximately at the same time. And then we can aggregate those models at the same time without a long waiting time. However, in practice, the server does not know the client's computing power beforehand. And the computer power may also change during the training. So how to resolve this? Our solution is this. We add a computing power aware scheduler on the server side, and it basically does 3 things. The first thing is that it can estimate and update the computing power of each client on the fly based on their previous training history. And then we try to synchronize the arrival of the client local models by assigning different number of local steps according to the estimated computing power. And then the scheduler interact with the server-side aggregator to update the global model using one or a group of synchronized client local models. And with this solution, when we train some machine learning model on heterogeneous data, we can see that these pink and purple and orange curve are variants of this algorithm, can achieve much higher accuracy than the asynchronous algorithm, which are the blue one, and this which are the right one and the light blue one. It can achieve better accuracy, and it is much faster than the synchronous algorithm, which are this dark blue one and the green one. In addition to heterogeneity, there are also some security and privacy concerns in federated learning. So federated learning, even though it does not share the model parameters directly, itself is still not privacy preserving. The training data can be reversely constructed from the model gradients. And we show the example. So from this subplot A, we can see that we can, without any further privacy preserving techniques, we can reconstruct the training image very well, just using the model gradients. So there are a lot of differential privacy algorithms are proposed, which add some noise to the model parameter. And this can significantly increase the difficulty of the reconstruction. So when we increase the difference privacy budget, we can see that the image reconstruction quality gets lower and lower. And finally, it can just, it only get noise signals when we use very, very large different privacy budget. And as it is also shown here, the MSE of the reconstruction image and the original image is getting larger and larger when we apply the differential privacy with larger budgets. And there are also other type of security concern is that some clients may try to attack the FL training process by sending some poisoned update for the aggregation. So if there are some hackers want to attack one federated learning experiments, they can either using some garbage data to train the model parameter, or they train using good quality data, but when they send the model parameter, they just send some random parameters to the server, and this random parameter servers are used in the global aggregation and cause the global model to become garbage as well. So there are some algorithm solutions, which include for the server, we give it a small central validation data set that no clients have knowledge about it. And we use this validation data set to validate each local model sent from clients. And we see the if a certain client local model performs so bad on this central validation data set, we just drop it from the central aggregation, and this helps us to protect the federated learning. Also, from the system level, it is also important to build a secure and trusted federation so that only clients that everyone trusted with each other can join this experiment. And this can also help us to avoid the attack of the FL experiments. Another thing is the setup of federated learning is kind of difficult because federated learning is a distributed computing paradigm. So setting up FL experiments can be tedious for domain experts. As I mentioned, right, federated learning is mainly for certain domain where the data privacy is important. Like for a medical person, if you ask him to set up a distributed training experiment, setting up a server and connecting to the server and orchestrating the whole process, they just feel, oh, it's too hard for me, then I just give it up. So all these difficulties make the barriers to entry for leveraging FL federated learning in their work is relatively high. And our solution is try to provide federated learning as a service for domain experts. And here's our solution. We created a web platform for domain experts, and the user can log in this web form using Globus, using their institution credentials. And after their login, they will be directed to a dashboard, and where they can create a federation, or say FL group. And within this federation, they can invite collaborators using their institutional credentials, like their institution email. With this, they know that who they are collaborating to, and they can trust each other. When the collaborator accepts the invitation, they can set up a Globus compute endpoint on their computing machine. And then the collaborators just need to provide this endpoint ID as well as a data loader for their private local data. And that's it. The job for collaborator is done. And for someone within the group, created the group and want to serve as this group administrator, they can configure and launch FL experiments using the website we gave. So within the server configuration page, they can visualize what is the data distribution of the clients, what is the endpoint status, and then they can specify what type of federated learning algorithm I want to use, specify the model architecture, loss function, and all other hyperparameters, including the privacy budget. After the server set all this up, they just need to click a button, and we will launch the FL experiment for them. So when they start the experiment, our service will launch an AWS EC2 container to serve as the FL server and orchestrates the whole federated learning process with the client computing resources. And for all the training logs, results, we will store them back to the AWS, and all this can be visualized via our web platform. So we can show you some picture. So after a person log in, they will be directed to a dashboard where they can create a federation, or they after they join the federation, they can also see those site information. When they join federated learning as a site, they can also see their site information. And if you are a server, you can create a new experiment where you can configure the experiment. You can see the client endpoint status, select what algorithm you want to use, give experiment name, setting training epochs, and setting privacy budgets, and so on. And after the experiment finish, we will generate a federation report for the clients, which includes all the training parameters they use, what is the site validation accuracy throughout the training process, and so on. So with this service, this makes it much easier for domain experts to launch an experiment, because the only data they need to write is a data loader to their local data, and that's it. And after talking about this, I would like to introduce our effort in building a framework for federated learning, and our aim is try to resolve all the challenges we mentioned in the previous presentation and use it to backend our federated learning as a service. And here is the framework overview of our framework, and our framework is called Advanced Privacy Preserving Federated Learning Framework, or APPFL. So basically, we create agents and for the FL server and clients. So for the server agent, it comes with a server configuration file, an aggregator with some privacy module to further provide the privacy of the training data, a scheduler to allow different synchrony of the FL experiment. It can be either synchronous or asynchronous, and some other task handlers, which can do some other things in addition to the aggregation job. For the client agent, it also comes with a client configuration. It has the client agent has the access to its private local data, and those private local data will be loaded by the trainer to train the machine learning model. And the server agent and client agents exchange requests and response for aggregation and other tasks where a central communicator. The communicator also comes with some configuration file and as well as authenticator to build a trusted federation, task controller for exchange task information, data connector for exchange large model parameters, as well as some compressor for user to optionally compress the data to improve the communication efficiency. And now we can introduce these modules one by one. So for the server config part, the server config part is a simple YAML file composed of two main parts. The one part is client configs, and you may find this is confusing, right? This is server config, why it contains a part called client configs. This part basically includes the configurations that the user want to share among all the clients. For example, the module architecture to use, what type of trainer to use, what is the learning rate, what is the number of local steps, and so on, which will be shared with all clients at the beginning of the FL experiments. And this can help us make the experiment coordination easier. And the second part is server configs, which are the configurations for the server. For example, the type of scheduler, the type of the aggregator, and so on. So on the right-hand side, we show an example of the server config YAML file. So at the top, we have client configs, which contains like server config, what trainer to use, what is the trainer mode, step or epoch, for several step or several epoch. What is the loss function? What is the model parameter? What is the configuration parameter? And for the server config, we choose synchronous scheduler. We use fed average aggregator, which essentially average the model gradients from different clients. And for the client config, each client has another YAML file which contains configurations specific to one certain client. For example, the data loader file to load the sensitive local data. What is the device type, whether you want to train using CPU or GPU, or it can be auto if you want to use utilize all available GPUs, and some logging settings, as well as the communication settings. For example, if you use gRPC for the communication, what is the server URL that you should connect to, and what is the maximum message size you would like to send. And then let's talk about the aggregator. So aggregator is used for aggregating one or more client local models to update the global model. And depending on the synchronity of the FL algorithm, the aggregator can take only one client model to update the global model for asynchronous federated learning algorithm, or a list of client local models to update the global model for synchronous algorithm, or one or a list client local models to update the global model. These are for other types of asynchronous algorithm, like the one that we mentioned, right? We use a scheduler to try to synchronize the arrival, right? If we can synchronize the arrival of several client local models, then we aggregate it using a group of client local models. And if we fail to do that, then we just update the global model using one client local models. Our framework supports several available aggregators, And this aggregator supports some advanced algorithm to deal with data heterogeneity as well as device heterogeneity. And there are some other aggregators that can further protect the privacy of the training data. And then we can talk about the scheduler. The scheduler is the interface between the communicator and the aggregator. So whenever the communicator receives a local model from a single client, it directly hands the local model to the scheduler, and the scheduler will decide when should I pass this local model to the aggregator to update the global model. So currently we support 3 types of scheduler. For synchronous scheduler, it will cache the models and pass all the models after it's receiving the local models from all clients. For some naive asynchronous scheduler, it will pass the model once receiving it. For compact asynchronous scheduler, which is the one that I introduced before, it will do things more wisely to wait for a group of clients which are supposed to arrive almost at the same time, and then pass this group of client local models to the aggregator for aggregation. For the trainer and privacy part, the trainer trains the local model using the local data loader, and it needs to define 2 basic functions. One is train, which trains the local model, and the second one is get parameter, which is used to return the parameters that are needed by the servers at aggregator. And this can be the model state dictionary, the model gradients, and the prime or and due states for some privacy preservation federated learning algorithm. Well, for the privacy module, it contains various privacy preservation algorithms to prevent training data reconstruction. And for the authenticator, this module helps us to create a trusted federation to ensure the security of the FL experiments. And APPFL currently supports Global's authenticator. As you can show here, APPFL comes with a command line interface. And when you type APPFL auth, then it will ask you to select whether you want to authenticate, you're authenticating for the server or the client, and you can select one. And in this case, the command line told me that I already logged in, and then I can either log out or change to another account or exist. So I try to change another account. And in this case, this command line will give me a web link, which I can connect to. And when I go to this web link, it will give me some authorization code to paste. And I can just paste it to the command line. And after that, I successfully authenticate myself as a federated learning server. So only clients within the same Globus group, so after login, only clients within the same Globus group are authorized to join the FL experiments. With that, you know who you are in your group, and this helps you to ensure that no one in your group will, maliciously attack the FL experiments by using some poisoned data or model. So this further helps to ensure the security of the FL experiments. And for the task controller, which are used to send task signals between the server and clients, like what task I want the server to do or what task I want the client to do. So there are 2 essential types of communication control signals. One is client-driven and one is server-driven. And what does this mean? So on the left-hand side figure, this shows client-driven communication. And the first step is the client performs local training, and then it requests global model aggregation to the server by sending my local model parameter. And then the server performs the global aggregation and send back the aggregated model. So you can see in this case, it is the client initiate a request to the server. And there are other type of communication, which is called server-driven, where server controls the whole FL process. The server first sends a task signal to the client to local training task signal to the client to ask the client, I want you to do local training on your site using our local data. And second, the client perform local training using the local data and then send the locally trained model as a result of the task back to the server, and the server aggregates those local model. And in this case, it is the server initiate the local training at the client side. So in our framework, we use gRPC for client-driven communication. It is essentially clients send a remote procedure call to the server to do the aggregation or other types of tasks. And we use Globus Compute for server-driven communication. And Globus Compute is kind of like a function as a service platform where the server can say, I want a specific client to run this Python function for me, which do the training, and then I can collect the results back. And for the data connector, we integrate with proxy store. And what this data connector do is basically it is used for transferring the large model parameter between the server and the clients. Because in some of the like task controlling signal communication protocol, like Globus Compute, it has limitation in the parameter size. It only allows 5 megabytes of parameter, so which is far insufficient for machine learning models. You know, nowadays, typical machine learning models are several, like at least tens of megabytes or hundreds or even gigabytes. So Globus Compute itself cannot transfer that amount of data. So we need to ensure that there's some way to securely and robustly transfer the large model parameters. And we use proxy store to enable user to do this. So proxy store, it is not a protocol, but it is kind of a way for user to integrate any type of data transmission protocol they would like to implement. And now it supports Globus transfer to transfer the data between 2 different sites, or transfer data using a relay server, or transfer data using AWS S3. So these are supported, but user can easily add in any data transfer data transfer protocol they would like to use. For example, if you within a local network, there are certain ways to enable more efficient data transfer, and user can implement these more efficient data transfer themselves. And the final module is compressor. So we have compressor seamlessly integrated into APPFL to do lossy and lossless compression in the transferred model parameter. And this compressor also comes with easy installation. So we also provide a command line interface for this, where you can run APPFL install compressor, which will build a C source code of this compressor on the client's local machine. And the compressor can be used within APPFL to compress the model parameters to increase the communication efficiency. And the compressor can also be used in a standalone manner as well. So in this example on the right-hand side, when you do from APPFL compressor import SD2 compressor, and you define a convolutional neural network, and you use some compressor configuration, then you can use this compressor to compress that model in a standalone manner. So now it's time for a demo. But before we go into the demo, let me briefly discuss the configuration for this demo. So as we mentioned, in our framework, there are 2 types of inputs from user. One is server configuration file, and one is client configuration file. And here we will show what this configuration file looks like in our demo. So we first take a look at the shorter client configuration. The training configuration, we use CPU on my local computer. We set some login ID for this client. And for the local data set, essentially, I write a minutes dataset data loader, minutes data.py data loader file, and within that file, I get a function called getMinutes, and then I pass necessary keyword arguments for it. Like there are 2 number of clients, and I am client 0, and I use some non-IID partition strategy to partition this minutes dataset. I try to visualize the distribution. And for the communication configuration, I use gRPC, and I connect to my server at localhost at port 50051. And then for the server configuration file, as we mentioned, it is composed of two parts. One is server configs. In this part, I use synchronous scheduler. And in the scheduled configuration, I said there are two clients, and they are required to have the same initial model to start the training. I use the Fed average aggregator, and I assign the same weights to the client local models. I use CPU for my server. The number of global epochs is 10, which means that there will be 10 rounds of local training and aggregation. I also set up some logging and communication configurations. In addition to the server config, I also the server config YAML file also have some general configuration for the clients that I want to share to all the clients at the beginning of the training. It contains the train config, what type of trainer I want to use, what is the mode I want to do stepwise, and each client do a handled number of local steps. I use Adam with learning rates 0.001 in local training. The server define a loss function locally, which is cross entropy loss, and I will send this loss function to the clients as well. I want to do validation after each local training run, and also do pre-validation before each client train their local model. I also provide a metric. I also provide a metric function to evaluate the model, the trained model, in addition to the loss. I disable the differential privacy in this case. For data loader, I want to use a batch size 16 for training data and batch size 16 for validation data. Shuffle the training data and do not shuffle the validation data. For the model config, I provide a Python file which defines the model architecture of the model that I want to train. And for the communication, I do not want to use compression in this case. So now we can start the demo, and the demo is available at, it is called APPFL Sign FM. And here we show the step of this demo. It is essentially clone the repository and build from the source code, and we create a demo folder. And when we, and then in the demo folder, it has a run shell script which can run the demo. So now let's start the demo. So, okay. So in this case, in this run script, it is pretty simple. It basically runs three Python command in the background at the same time. One is run server, which launched the server, a gRPC server, and it launched another two run client function with different client configuration. And all these two clients will talk to the server I launch, and they will perform federated learning. And let's get started. Let's go to the demo repository and run it. So in this terminal, it will output both the log for the server and clients because I run this at the same time. But here's a, but it also provides log for both the server and clients in separate files. So we can see that in addition to the log file, it also generates some visualization file, which shows the data distribution for client 1 and client 2. And for the server file, it shows that it can receive like a get configuration request from different clients, get initial global model, and during the training, it received update global model requests from different clients. And for the client side, it will show the training process with some validation results. So maybe we can talk about the first two lines. This line is run 0. Pre-validation means that we validate the model before we train things. At the beginning, we get very low accuracy, which is fine. And after local training, we can see that the training accuracy is pretty high, but the validation loss is still high as well, and the validation accuracy is not good. This is because we partition it in a non-IID way. So even though the local training get very good accuracy on the local data set, it does not perform well on a holdout validation data set. So this is why we need to do federated learning. And we can see that throughout the training, right? Let's see epoch 6. So epoch 5, at the end of epoch 5, the local training gave accuracy 98 something on local data, but it's just 68 on global validation data set. But after we do the validation, and when we validate again at run 6 at the beginning, we can see that the central aggregation helps us to get a more robust model to have global validation accuracy of 91. And this shows the power of federated learning. And I think that's it. I think I go faster than I expected, but this is a demo, and now I think it's question time. I think we're on time of the original end time, which is 12 p.m. So any questions? Yeah, about 15 minutes for questions.
Yeah, great. Thanks. This is really amazing work. Maybe for the demo, and maybe also talking about this entire project that you have. Right? So, do you imagine that for like in HPC, right? Do you imagine that each HPC resource, right, might have like a way to like keep a training model, like so that people can leverage that to decide, you know, which sort of because if you notice, right, so all the leadership computing facilities, right, all maintain logs of output, right, and so I wonder if there's some opportunity there in terms of organizations keeping you know, models that they can share across. How are you thinking about how does this get implemented in practice between different organizations?
Yeah, like you mean, so I understand, like after training, how can we like store and host it and use this global trained model to, you know, for usage at different organizations. So this is a good point, and our roadmap here is that we want to create a way that we store like the global model somewhere, maybe our current plan is somewhere on the cloud, and then we can we should allow all the clients within the same federation get access to the model. And we also want to create a tool which can directly host that model either on the cloud or on their local machine by downloading it. And then all the user within like within the federation can utilize that model by downloading or the cloud hosted model, or even using the cloud to host that model. And like we can generate some like tokens that only authorized user can utilize this model for inference tasks and so on.
Okay, great. Here or in the audience there. And this demo, we'll put it up on the site. Some school.
Yeah, I saw that there's a repo.
Yeah,
I can.
We'll get there.
I can also share the slides if you know.
Is how you can coordinate between facilities and all that, right? The initial like startup cost.
Oh yeah, this is a really great question, and this is kind of related to like the task communication pattern I mentioned, which is there are two types, right? One is client driven and one is server driven. So if you use gRPC is like client driven. Different clients should start almost at the same time to connect to the server, and the server, like, so for the servers, say if when I configure, I have 5 clients that I'm expecting, then I only distribute the initial model when I get connection from 5 clients. And this can be a tedious job because the problem is this. On HPC, you have queues, right? You never know that when you get a queue. available for you. And it is very hard to have like 5 to 10 clients having available resources at the same time. And this really makes like gRPC or other types of client-driven communication very hard for the coordination. And that is why we have server-driven communication. Server-driven communication, we use global compute. And how global compute works is that user can install global compute endpoints on different HPC, and user can configure these endpoints according to what job scheduler you are using. For certain HPC, they use Slurm, so you can specify like what is wall time for this, how many CPU, how many GPUs I want to use, and whether like there are some initial scripts like what kind of module you want to use when you start this endpoints and so on. And also for Polaris, I'm not sure whether you guys know it, it uses PBS. And it has another provider or like provider in writing the configuration file. So when you install all these endpoints on the supercomputer, it will first it will start a daemon process on the login node without allocating any computing resources. And then whenever you send task, when the server initiate task to these clients, then this global compute node receive the task, and then it will start allocating computing resources for this task. So in this way, of course, right, different clients may still need to wait for the allocation to start. But in this case, there are no clients involvement. Only the server need to do the things, and even though like some are queued, then the server just waiting. This just makes the coordination much easier because there's only the server itself trying to start the training task. So with that, and also another point for global compute is that when you get started, then it will continue, right? For a long time, and whenever the experiment gets started, then everything can go smoothly. So there are just some initial waiting for a queue at the beginning, but without any client involvement. So it just makes the coordination easier. And that's the reason why we try to integrate global compute. Because for most of the federated learning framework developed by other groups, they essentially use gRPC, and it's client-driven, and it requires client to to study some Python code almost at the same time. It makes the coordination very hard. And but with global compute, just the server start a script and wait. We may waste some time, but at the beginning, but at least it saves a lot of time for the human, and that's the benefit.
In like the extreme case of like one client starts and finishes, and the next one starts and finishes, because scheduling nonsense, how does that like impact training quality, or does it? Like, is it necessary to have all of them at some point be running concurrently, or if it like in the worst cases, like total synchronization inside?
Yeah, like actually this depends on like what algorithm works. If like it is for synchronous algorithm, the impact is that it makes the whole process pretty slow. Like if client one finish, it sends back the local model and it becomes idle. Maybe like its wall time is finished and it's still there. It's fine. And then client two will finish after a long time, and then the server just wait. It wastes some time. And for asynchronous algorithm, then it is totally fine, right? When the server, when the client finishes, send to the server and get back the updated model almost immediately, so it can continue the training. But the problem here is that you may get some like the drift of the